Alright, in keeping with the earlier theme of pool, here's a little example about J-Random Troll hustling some chump. After intentionally losing a couple of rounds, J-Random offers to raise the stakes. The opponent, feeling extra confident, agrees to do this, and J-Random uses his physics knowledge to sink the shot. So as seen from above, when J-Random Troll hits the cue ball in the positive y direction, you're looking at the table from above, so currently positive y does not mean vertical. It's simply one of the two directions on the table, length or width. He hits the target ball at a velocity of 4.2 meters per second, and they collide elastically. That means they bounce perfectly off of each other and even conserve kinetic energy. The cue ball moves off at an angle of 42 degrees to the left of the vertical, and it has a final speed of 3 meters per second. So what's the final speed and angle of the target ball? You're going to assume that they have the same mass here. So here's a little animation that I lovingly put together for you all. Here's a cue ball. It's traveling with an initial velocity of 4.2 meters per second toward a target ball. They collide, and the two go off in different directions. We know a little bit about the cue ball. Now we're trying to figure out about the target ball. What is its final velocity, and what is its direction? What is its angle away from the y-axis, as seen here, the vertical? Well, this is just a good old two-dimensional conservation of momentum problem. Well, the initial x momentum of the cue ball, I'm going to denote that with a little c here, plus the initial x momentum of the target ball is going to equal the final x momentum of the cue ball plus the final x momentum of the target ball. This means my total system is considered the cue ball and the target ball together. And the grand total x momentum of the system is the same before and after the collision. Well, that's telling me that the initial x velocity of the cue ball times the mass plus the initial x velocity of the target ball times the mass will equal the final values of both of them in the x direction. Well, looking back at my setup, the cue ball is only moving in the y direction, which means, oh, I swapped these two letters. It's the same thing. The initial cue ball's velocity in the x direction is 0, and the target ball wasn't moving at all, so both of its x and y initial values are 0. So that means I can cross out this one to be 0, and this one to be 0. All right, the entire left side of my equation is 0. So that means it equals mass times the final velocity of the cue ball in the x direction plus mass times the final velocity of the target ball in the x direction. Well, looking back at my picture, the cue ball has a final velocity of 3 meters per second at an angle of 42 degrees away from the y-axis. That means its x component is going to get the sign. So v final of the cue ball in the x direction is going to be 3 times the sine of 42 degrees. And that comes to just about 2 meters per second to the left. Since it's to the left, I'm going to plug in -2 and call my leftward direction negative. Okay? When I solve for the final velocity in the x direction of the target ball, I can add the -2m over to the other side, make it +2m, cross out the masses because they're the same. At this point, I should probably take a second to let you know, believe it or not every two objects that collide together have the same mass. Shocking, I know. But in this particular example, they do. So that means not every velocity in the x direction will be the same before and after, but in this example, they are. So my final x velocity of the target ball is 2 meters per second as well. Now do take note, that's only the x velocity of the target ball. That's not the total velocity. We got to look in the y direction as well. All right, this is telling me that my initial momentum in the y direction of the cue ball plus my initial momentum in the y direction of the target ball is the final value in the y direction of both of these together. So currently I've plugged in the values that I already know. I know my initial momentum in the y direction from the cue ball is 4.2 meters per second times the mass. I know that the target ball was not moving in either the x or y direction, and then I've just left my final values as variables for right now. If I go back to the picture, I can discover a little bit about the final y value of the cue ball. Since it's adjacent to this 42-degree angle, that means VQ final in the y direction is going to be 3 times the cosine of 42 degrees. And that comes to about 2.23 meters per second. So I can plug that in to this value right here. So it's mass times 2.23 meters per second. And now all I got to do is solve for the final y velocity of the target ball. The mass, once again, is going to cancel out of each and every term. When you divide one side of the equation by a value, you have to divide every term on that side of the equation by that value. And I'm left with 4.2 equals 2.23, both of which are positive because they're both pointing in the upward direction, at least the way that I have it drawn on my pool table. And I just need to solve for this one by subtracting 2.23. I ultimately end up with 1.97 meters per second for the y component of the target ball's motion. So adding that into what I already know about the target ball, I know that its final velocity is 2 meters per second in the x direction. I know its final velocity in the y direction is 1.97 meters per second. So I want to know what this angle is, and I want to know what the final overall velocity is of the ball. Well, I've basically set up a triangle where I've got the height and the base, and I just need the hypotenuse. For that, I can use the Pythagorean theorem. When I add these two values together, square them, and take a square root, I get the final velocity to be around 2.81 meters per second. To get the angle, I can just use some right triangle trig. The opposite side is 2. The adjacent side is 1.97, so I can slap a tangent onto that one, where the tangent of theta is opposite over adjacent. Now I just got to take an inverse tan, or an arctan, and I get about 45.4 degrees. So that's how conservation of momentum in 2 dimensions works. Cool.